force at a distance. This comes back again like why plasmas are so strange. It's the same thing here. And if it's immersed in this magnetic field, you're not actually physically touching it, but you're making a force go onto it. So that's the inherent feature of magnetic confinement. And then magnetic confinement devices are like a tokamak, are basically configurations which exploit the features of that magnetic containment. There's several features to it. One is that the stronger the strength of the magnetic field, the stronger the force. And for this reason is that if you increase the strength of magnetic fields, this means that the containment, because namely the force which you're pushing against it, is more effective. And the other feature is that there is no force. So for those who remember magnetic fields, what are these things? They're also invisible. But if you think of permanent magnets or your fridge magnet, there are field lines which we actually designate as arrows, which are going around. You sometimes see this in school when you have the iron filings on a thing and you see the directions of the magnetic field lines, or when you use a compass, right? So that's telling you north, because we're living in an immersed magnetic field made by the Earth, which is at very low intensity magnetic, but it's strong enough that we can actually see what direction is. So this is the arrow that the magnetic field is pointing. It's always pointing north. And for us, so an interesting feature of this force is that there is no force along the direction of the magnetic field. There's only force in the directions orthogonal to the magnetic field. So this, by the way, is a huge deal in a whole other discipline of plasma physics, which is like the study of like our near atmosphere. So the study of aurora borealis, what's happening in the near atmosphere, what happens when solar flares hit the magnetic field. In fact, remember I said fusion is the reason that life is responsible in the universe? Well, you could also argue so is magnetic confinement, because the charged particles which are being emitted from the galaxy and from our own star would be very, very damaging to on Earth. So we get two layers of protection. One is the atmosphere itself, but the other one is the magnetic field which surrounds the Earth and basically traps these charged particles so they can't get away. It's the same deal.
How do you create a strong magnetic field?
Yeah. So
with a giant magnet.
Yeah. So it's basically true.
Engineering is
there's
awesome.
essentially two ways to create a magnet. So one of them is that we're familiar with, like fridge magnets and so forth. These are so-called permanent magnets. And what it means is that within these, the atoms arrange in a particular way that it produces, the electrons basically arranged in a particular way that it produces a permanent magnetic field that is set by the material. So those have a fundamental limitation how strong they can be, and they also tend to have this like circular shape like this. So we don't typically use those. So what we use are so-called electromagnets. Mm-hmm. And what is this? It's like so the other way to make a magnetic field, also go back to your elementary school physics or science class, is that you take a nail and you wrap a copper wire around it and connect it to a battery, then it can pick up iron filings. This is an electromagnet. Mm-hmm. At its simplest, what it is, it's an electric current which is going in a pattern around and around and around. And what this does is it produces a magnetic field which goes through it by the laws of electromagnetism. So that's what that's how we make the magnetic field in these configurations. And the key there is that it's not limited by the magnetic property of the material. The magnetic field amplitude is set by the amount of the geometry of this thing and the amount of electric current that you're putting through. And the more electric current that you put through, the more magnetic field that you get. The closest one that people maybe see is one of my favorite skits actually was Super Dave Osborne it's probably past you. It was like in a show called Bizarre. Super Dave Osborne, which was a great comedian he was a stunt man, and one of his tricks was that he gets into a car, and then one of those things in the junkyard comes down, and picks up the car and then puts it into the crusher. Mm-hmm. This is his stunt, which is pretty hilarious. Anyway, but that thing that picks him up, like, how does that work? That's actually not a permanent magnet. It's an electromagnet. Mm-hmm. And so you can by turning off and on the power supply, it turns off and on the magnetic field. So this means you can pick it up, and then when you switch it off, the magnetic field goes away and the car drops. Okay, so that's what it looks like.
Speaking of giant magnets, MIT and Commonwealth Fusion Systems, CFS, built a very large, high-temperature superconducting electromagnet that was ramped up to a field strength of 20 Tesla, the most powerful magnetic field of its kind ever created on Earth. Because I enjoy this kind of thing, can you please tell me about this magnet?
Yeah, sure. Oh, it's fun. Yeah, there's a lot to parse there. So maybe we already explained an electromagnet, which in general is what you do is you take electric current and you force it to follow a pattern of some kind, typically like a circular pattern, around and around and around and around it goes. And the more current and the more times it goes around, the stronger the magnetic field that you make. Okay. And as I pointed out, it's like really important in magnetic confinement because it is the force that's produced by that magnet. In fact, technically it goes like the magnetic field squared because it's a pressure which is actually being exerted on the plasma to keep it contained.
Just so we know, for magnetic confinement, what is usually the geometry of the magnet? What are we supposed to imagine?
Right, yeah. So the geometry is typically is what you do is you want to produce a magnetic field that loops back on itself.
Mm-hmm.
And the reason for this goes down to the nature of the force that I described, which is that there's no containment or force along the direction of the magnetic field.
Right.
So here's a magnetic field. In fact, what it's more technically or more graphically, what it's doing is that when the plasma is here, here's plasma particles here. Here's a magnetic field. What it does is it forces all those, because of this Lorentz force, it makes all of those charged particles execute circular orbits around the magnetic field.
Mm-hmm.
And they go around like this, but they stream freely along the magnetic field line. So this is why the nature of the containment is that if you can get that circle smaller and smaller, it stays further away from Earth temperature materials. That's why the confinement gets better. But the problem is that because it free streams along, so if we just have a long straight magnetic field, okay, it'll just keep leaking out the ends like really fast. So you get rid of the ends. So you basically loop it back around. So what these look like are typically donut-shaped or more technically toroidal-shaped, but donut-shaped things where this collection of magnetic fields loops back on itself, and it also, for reasons which are more complicated to explain, basically it also twists slowly around in this direction as well too. So that's what it looks like. That's what the plasma looks like because that's what the fuel looks like. So then this means is that the electromagnets are configured in such a way that it produces the desired magnetic fields around this. So
how precise does this have to be?
You were probably listening to our conversation with some of my colleagues yesterday. So it's actually, it depends on the configuration about how you're doing it.
The configuration of the plasma.
The configuration of the electromagnets and about how you're achieving this requirement. It